Good day, everyone. My name is Jay, and welcome to the channel Papers with Jay. This is a new YouTube channel we're starting to discuss state-of-the-art papers in machine learning, computer vision, natural language processing, and so on. Today, we're going to discuss the paper called eDiff-I, text-to-image diffusion models with an ensemble of expert denoisers. Now, before we look at the paper, I want to take a minute to explain why we are starting this new YouTube channel. My name is Jay. I am an engineering manager practicing machine learning in one of the big tech firms in the Bay Area. Before I did my PhD in machine learning and has been working in industry for around 10 years applying machine learning to interesting problems. Now, machine learning has been experiencing tremendous growth in the last few years. Now, here is a plot that shows the number of papers that are published every year. So in the last 10 years, there was a 30x increase in the number of papers. And today, roughly around 100 new papers are published to archive every day. This becomes a big challenge for us because now it's really hard to read all these papers and then understand where the research and the field is moving. So this is the precise problem our YouTube channel wants to solve. So in this channel, we will discuss most of the interesting recent papers, provide really intuitive summaries so that hopefully you guys can just go through the summary and do not have to read all these papers. And if you really like a paper, of course, you can go back and read more. So thereby it can save you a lot of time. It can also help you understand these papers a lot more. If you like this channel, please subscribe, give me a thumbs up, and share it with your friends and your social network. All right, that's all about the intro. Let's get started. Now, so again, the paper we're going to discuss today is called eDiff-I, text-to-image diffusion models with an ensemble of expert denoisers. So this is a paper which can take text as input and then generate really pretty images like the ones shown here. Now, the paper is published by a bunch of folks in NVIDIA. And I also have an archive link to the paper here. This is a really new paper. So it was published in archive only a couple of weeks back, and it gives state-of-the-art results for text-to-image conversion. All right, now before we can look at this paper, I'm going to take a little bit of time to explain what diffusion models are. If you're already familiar with diffusion models, you can skip these slides and the part of the video. The slides I'm going to present on diffusion models are taken from a graduate course lecture given by Roni Sengupta. And if you want to look at those slides more, I have a pointer here. So what are these diffusion models? So basically, a diffusion process has two steps. One is the forward diffusion process. What this does is it progressively adds noise to your input signal. So if you look at the image here, we have a cat image here. We keep on adding noise to it in the forward diffusion process. So the image gets more and more noisy. And then in the end, you have a really noisy image with like no visible information about the cat. Now, the reverse diffusion process does exactly the opposite. It takes a noisy image. It tries to remove the noise so that we get a clearer image. So if you keep applying a reverse diffusion process, then you can take a noisy image and then get a really clean image from it. Now, what is the math behind the forward diffusion process? This math is not very important. but I'm still gonna mention it for completeness. Now, basically, you're applying noise to an image multiple times. So these images are represented by variables x0, x1, x2, and so on. Now, typically, you add Gaussian noise. So you can write your noise image xt as a Gaussian representation on top of your less noisy image xt minus 1. Now this is the equation here. So xt can be written in terms of xt minus 1 plus some noise that's added, which is this epsilon t minus 1. Now, one interesting result is that you can write the teeth noise image xt in terms of your zeroth noise image x0. Again, in a very similar form. So xt is a constant times x0 plus some noise. This equation is interesting because we'll use that later on. But all you want to understand from this slide is you're progressively adding noise. Typically, you model noise as a Gaussian noise. So you can write your noisy sample xt as a sum of your previous sample xt minus 1 plus some noise. And your really noisy image xt can also be represented in terms of x0, which is an interesting result we'll use later. Now, what is really interesting is not the forward diffusion process, but the reverse process, because that's going to take some noise and then try to get a clear image from it. Now, typically, the way we do it is by using a neural network. So given a noisy image, you will train a neural network, which will help you get the noiseless image. Now, the neural network we use for this is the UNet architecture. So UNet architecture typically consists of two pieces. One is an encoder here, and the other is a decoder. Now, the architecture takes an image as input, and the encoder applies multiple convolution layers. As you go deeper in the encoder stack, the spatial resolution decreases, whereas the channel resolution increases. Now, the goal of the encoder is to capture the useful information in the image. The decoder takes the encoder output here as its input, and it does the reverse process. So as you kind of go deeper in the decoder stack, your spatial resolution increases and your channel resolution decreases, and eventually it predicts an image's output. So depending on the input and ground truth image you give to a unit, it can predict multiple things. It can do denoising, it can be used for segmentation, and so on. In our case, we give a noisy image as input to the unit. We make it predict the noise in the image here. And then once you know the noise in the image, you can subtract it from the noisy image, and hopefully you will get a clean image. So this is the whole idea of the reverse diffusion process. So we take the noisy image, make a unit predict the noise in the image, subtract it from the noisy image, and then we get a clean image. Now, let's look at how you can train image diffusion models. So I have the steps here on the left. You first take a clean image from your batch. You decide the steps of noise to apply, which is the variable t here. Now, given the input image and the step, you now generate a noise epsilon by using a Gaussian process. And then you compute your noise image. This is by using the expression here. So noise image xt is a constant times x0 plus another constant times your noise epsilon. This is the same equation we saw in the beginning. Now that you have the noise image xt, you make the neural network predict the noise, which is epsilon theta times xt. Now, to train your neural network, you need a loss function. The loss function is shown here. Even though this looks complicated, this is pretty easy. Basically what it does is it looks at the real noise epsilon. It looks at the predicted noise epsilon theta of xt, and then you take the L2 norm, and that is the loss you're going to optimize. And then of course, now that you have the loss, you can do gradient descent to update the weights, and then you do it till convergence to get your trained model. So that's all about the training process. Now let's look at the inference process. During inference process, you have a trained model and you have a noisy image as input, and your goal is to predict your clean image, which is basically the reverse diffusion process. Now, how do you do inference? You first generate your noisy image by using a Gaussian noise, right? So basically you generate your noisy image, which is just a Gaussian noise of the size you need. Now, now that you have the noisy image, you can apply your model to predict the noise, and then you can subtract the predicted noise from your noisy image, and then you do it multiple times till you get a clean image. So again, the inference is shown here on the right. So you first predict your noisy image xt, we're using a Gaussian noise. Then for t iterations, what you do is you predict your noise using the neural network, which is epsilon theta of xt. You subtract it from your noisy image and then do some scaling to get your cleaner image in one step. And then you do it t times, and then finally you return your clean image. So if you learned a good neural network, as you go through with the subtraction, it should generate a cleaner and cleaner image, and then finally you should get the really clean image. This is how you do inference with an image diffusion model. Now, till now, we were looking at diffusion models for denoising. Now, in this slide, we're going to look at diffusion model for text-to-image conversion. So these text-to-image diffusion models also take a noisy image as input. They also use a UNet as their architecture. They also predict some noise, which you can subtract from your noisy image to get your clean image. The main difference of these text-to-image diffusion models with denoising models is that these text-to-image diffusion models also take a text as input. So here we have a text saying a panda driving a bicycle in the woods with tall trees and sunlight. So we take the text also as input, and then we extract some embeddings from the text, and then we use that to affect the output of your neural network, and this is what is called conditioning. So basically the text embeddings condition the output of your neural network so that you get a noise which, when subtracted from your input image, you will get a clean image which also matches the text. And the typical way you condition using your text input is by using cross attention layers. So cross attention basically capture similarities between your text input and your layer output of your UNet, and then you can train this network so that the similarity between the text and the output image increases. If you don't understand cross attention well, I will have a future video where we talk about attention a lot more. Now, till now, we were just giving, we were mostly discussing, we were discussing diffusion models. Now we're going to go into the paper. So the paper has three interesting results. First is that it can take a complex text input and then predict a photorealistic image based on it. So here's an example. So the paper can take a text input like a highly detailed digital painting of a portal in a mystic forest and a person standing in front of the portal. So it can take that as input and then generate a really high resolution image which matches this text. Now, the second result in the paper is the eDiff-I algorithm can also take a text as input and a style image as an extra input, and then it can predict an output matching both the text and the style. So here's an example. So we have a text saying a photo of a duckling wearing a medieval soldier helmet and riding a skateboard. We also take a style image here, which is basically an image of a dog having this like kind of metal style. And then you get an output of a duck, which matches the text, but also has very similar style as the style image. So that's the second main result in the paper. The third result is this paper can also take a layout image as input. So this layout image will have a rough outline of the output you're looking for with some text in each outline. And it can also take an extra text as input. So here the text is a digital painting of a half frozen lake near mountains. And then you also have a layout image where you roughly draw the outline. And using both of this, it can generate an image which matches the text and the layout. And this is the first paper which conditions output on a layout image. So that's very cool. So now let's look at the technical contributions of the paper. Of course, this paper gives state-of-the-art results for text-to-image diffusion. And the reason for the state-of-the-art results, the main reason is because it uses an ensemble of expert diffusion models instead of using a single diffusion models. So what does this mean? So all the previous papers just use a single diffusion model for generating image from text. But the authors here make a key observation. So the observation is that this diffusion model behaves differently at different noise levels. In the beginning, when you have really high amount of noise in your input image, the diffusion model mostly uses the text for denoising. Whereas in the later stages, when you already have a very clear image as input, the diffusion model mostly uses the features in the input image for denoising, and it completely ignores the text. Now, in the next couple of slides, we will present some empirical evidence the authors provide for this observation. But assuming this observation is true, then instead of using a single diffusion model for all noise levels, you might as well use different diffusion models for different noise levels. So that way each diffusion model can capture the behavior at that noise level well. And this is the whole idea of the paper. So instead of using a single diffusion model, you will use 3 diffusion models. One for the low noise region, the other for the intermediate noise region, and the other for the high noise region. The nice thing about this is this does not increase your inference computational complexity because the number of inferences you do would be exactly the same. Now, the first empirical proof for this observation is in this slide. If you don't understand cross attention and if you don't follow this slide, that's totally fine. But I'm going to add this here for completeness. So in this slide, what the authors do is they look at the attention maps generated by their model. And there are 3 different attention maps. One is a self-attention, which is capturing the attention of the output image with respect to itself. And the other is the cross attention, which is capturing the attention between the text and the image. And because they use 2 different encodings, which we'll see later, the authors are looking at the cross attention using both the T5 text encoding and also the clip text encoding. Now, in this plot, if you have a dark red spot, that means there is strong attention. And if we have a light yellow region, that means like weak attention. So at first, the first column is at sigma equal to 80, which is the really high noise region. So at high noise, they see that the strong attention is always between the text and the image, which means that at the high noise region, the model is mostly learning attention between text and image. Whereas if you look at the really low noise region, which is the fourth column, Here, most of the dark red regions are between the image and itself, which means that at the low noise region, the model is mostly learning attention of the image with itself. Now, again, if you don't follow cross attention and this slide, that's totally fine. We're still going to understand the whole paper well. Now, this is the second empirical proof for this observation, and this is much easier to understand. So I would encourage all of you guys to understand this slide better. So in this slide, in the left image here, you're just applying taking a single text, which is this DSLR image of a lemur wearing a red magician hat and doing magic tricks with cards, right? So if you just take this as your text and then apply a text-to-image diffusion model, this is the output you get, which matches it, right? It's a lemur. Lemur has cards in his hand. Now in the second image here, you apply the text for 93% of the denoising, and for the last 7% of the denoising, you change the text to the new text, which is here. This is a DSLR image of a cute lion cub in a bowl of honey. And what you see is that this doesn't change the output at all. So if you change the text very late during your denoising, it doesn't change the output at all. This means that your denoising model is not using the text during the later stages of denoising. If you change the text after 70% of denoising, you get the lion face instead of the lemur face, and you get honey bowl instead of cards. If you change the text after 40% of denoising, the output pretty much just matches the final text. So it's going to be a bowl of honey with a lion cub in it. And if you change the text at like if you use the text for the whole 100% of denoising, then you again get a bowl of honey with a lion cub in it. So what this shows is during early stages of denoising, the model uses text a lot. So if you change the text early on, that affects the output a lot. Whereas during the latter part of the denoising, the model ignores the text and then just uses the input image for denoising. So this strongly explains the observation of the authors, and that's the reason why they use different denoising models at different noise levels. Now, the second main technical contribution of the paper is that instead of using a single encoder to capture the text, they use an ensemble of encoders. So for the text, they use the T5 encoder. They also use the clip text encoder. And for the style and layout images, they use the clip image encoder. And the intuition behind this is that T5 text encoder mostly captures the fine-grained information. So it's useful to make sure that your image output is very rich. Whereas the clip text encoder captures similarity between the text and the image, and it helps with the global layout of the image. So this is a key observation in the paper, and I'm sure that most of the future papers are going to use multiple encoders. And the third key technical contribution of the paper is that it has this like new way of conditioning your output using a layout image, and this is the first paper which introduces this new condition. Now let's look at how we can train this ensemble of expert denoisers. So again, just to iterate, because this is a key point, this is all based on this observation that the diffusion model behaves differently at different noise levels. Now, how does this ensemble of expert denoisers look? So here is a really interesting visualization. So here, as you are going from left to right, you are denoising your image more and you're getting a clean image. So existing papers use the same denoising algorithm for all the noise levels. Whereas eDiff-I, as shown here, uses one model for denoising at the high noise level here, a different denoising model at an intermediate noise level, and then again a different diffusion model at the low noise level. Now, Of course, the advantage of doing this is that it doesn't increase your inference complexity because you're doing the same number of inferences with the same sized model. But of course, this increases the training complexity. Now, instead of training a single model, you have to train like 5 models. Now, to reduce the increase in training complexity, the authors have a really good idea here. So they just train a single diffusion model for all noise level first. Then they fine tune this diffusion model at different noise level. So thereby, you're not increasing your training complexity a lot. Now, you can do this same process multiple times and get any number of expert denoising models. But in the paper, the authors just train 3 experts. So there is 1 expert diffusion model at low noise level, 1 for intermediate level, and 1 for high noise level. They're all done by first training a single diffusion model for all noise level and then fine tuning it for your noise level. So if it's a low noise expert, you will fine tune it using low noise samples. Now, of course, once you have your your diffusion model training scheme, others also use different inputs to condition. So for the text itself, they use different embeddings. So in this deck, we look at the conditioning signal. So the authors use multiple embeddings to condition. For the text itself, they use the T5 text encoding and the clip text encoding. And then to condition on the style or layout image, they use the clip image encoding. And the conditioning is all going to be the same. You are going to extract the embedding from your conditioning signal, and then you will condition your UNet by using cross attention layers. And then once a UNet predicts a noise, you subtract it from the noisy input image to get the clean image. Now, how do you generate high resolution images? Most of the diffusion models papers do not use a single network for getting the high resolution image. They typically do this in stages. So at first you take your input noise and then use a base diffusion model to generate a 64 by 64 image output. Now you take the 64 by 64 output as your input and then train a super resolution model to give a 256 by 256 output. You do the same now using a second super resolution model to get your 1024 by 1024 output. This is a standard trick which is done by pretty much every diffusion model paper, and all of these networks have the exact same architecture. It's just that the inputs they use are different. Now, to do paint with words, which is basically to use your layout image as a conditioning signal, the paper again computes cross attention between your layout and the text, and then uses it as a conditioning signal. Now we're going to look at the experiments. There are mostly 4 different types of experiments. Actually, 3 different types of experiments. One is to look at, so now we're going to look at the experiments. There are mostly 4 different types of experiments. One is to look at qualitative results with existing methods and show that the eDiff-I gives better results. We then look at quantitative results to show that the actual metrics are better with eDiff-I. We'll do ablation studies to show that using an ensemble of experts help, also using multiple embeddings help. And then the authors provide a lot of visual results for style transfer and also paint with words. So this is the first ablation study. Here we want to look at how an ensemble of experts are better than having a single model. So they do these experiments on 2 data sets. One is the MS COCO 2014 validation dataset, and the other is the visual genome dataset. Now, the results are presented in terms of a curve here. Now, the x-axis is the clip score, and the y-axis is the FID score. Clip score measures similarity between images and text. So if you get a higher clip score, that's better. Now, FID score is measuring the distance between your generated image and then natural images. So lower FID score is better, which means that your predicted images look really natural. Now, as you can see for both these data sets, at a fixed clip score, the FID score of the ensemble is lower, which shows that using an ensemble of experts help. Similarly, for a fixed FID score, the clip score is higher for the ensemble method. They do the exact same ablation study with multiple conditioning inputs using the T5 encoding and also the clip encoding. And they get a pretty similar result, like using both encodings give better results compared to using a single encoding. Mostly at these like high clip score regions. Now they do quantitative evaluation with existing papers. So some of the state of the art before this paper are imagined from Google, Stable Diffusion, DALI 2, and so on. So they compare their network with all of these, and then they show that their method have a lower FID score, which is kind of similar to the ones which Imagine and Party gets, but much lower than the other methods. They also present qualitative results where they look at their output with the output of other methods using the same text input. One of the things that's interesting with their method is it captures the finer text information better. Like for example, for that first text here, there is a phrase saying detailed fantasy image and 4K art station. And their output looks a lot more like art compared to the other two. So it kind of captures this fine-grained text information a lot more. This could be because of the T5 encoding that the paper is using. They also present a lot of style transfer results. So in these images, the first column is your reference image, which contains the style. The text here is the text input. The second column shows results using both the style image and text for conditioning. So here you have like two pandas walking on the road, and the style is very similar to that of the style image. The third column is if you don't use the conditioning with the style image, and then of course you just get a natural image. So it kind of shows that their way of conditioning using the style image works. Then they also show a lot of results for the paint with words case, where you have both a layout image and a text as input, and then their output pretty much matches the layout well. So that's all we have. We're reaching the end of this paper. So this slide is a one slide summary of the whole paper. So if you're just going to remember a single slide from this whole video, that should be this slide. So in this video, we present eDiff-I, which is a state-of-the-art text-to-image diffusion model. Now, the reason it gives state-of-the-art results is because of two reasons. One is that it uses an ensemble of diffusion models, where each diffusion model specializes on a different noise range. This is all based on the author's observation that diffusion models behave differently at different noise levels. So if you use different experts for different noise level, then you can capture the behavior much better. Also, the second reason why it gives state-of-the-art results is because it uses multiple embeddings to capture the text information. So they use both the T5 encoding and the clip text encoding to capture the text. Now, the third main novelty of the paper is that they also introduce a new way of conditioning your output using a layout image, and this is what they call paint with words. So this is again the first paper that uses this new way of conditioning your output. So that's all we have in this video. I hope you guys have enjoyed the video. If you like the channel, again, feel free to subscribe. If you have any questions or if there are parts of the video which is not clear, Please comment below and I will definitely go through them. And till we meet again, have a great rest of the day.